Okay, good morning everyone. So we have yet another snow day or inclement weather day upon us. Our unit test is going to be before the March break, so just so we don't waste any time, I'm going to put this video up on review of ionic bonding. It is all review from probably grade 9 even, grade 9 and grade 10, so should be pretty straightforward for you to follow along with. Okay, so first a little review. Valence electrons, remember, are the electrons found in the outermost energy level. The number of valence electrons typically corresponds with the group that element is in the periodic table. And we'll go through that in a second. So the reason why this becomes important is because all of chapter 2 and 3 we're going to be looking at how bonds are created, and the valence electrons are the ones involved in bonding. So just to recap, so everything in group number 1 has one valence electron. Okay, so please make sure you're following along in your note package as we go through this. So everything in group 1 has one valence electron. Everything in group 2, ignore that. Please be patient with me with this. Again, I'm using a mouse. So everything in group 2, the alkaline earth metal group, has two valence electrons. Now for the pattern that we talk about even from grade 9, right, we usually skip over this center block. So we go 1, 2, we skip over a few. So everything in group 13 has 3 valence electrons. Everything in group 14 has 4 valence electrons. 15 has 5. All right, so just to be helpful, right, take a look at the last number in that group number, right? So 15 has 5 valence, 16 has 6. Hopefully you're noticing a pattern here. 17, the halogen group, has 7. And then, of course, group 18 are our noble gases. So they all have a stable valence shell, or a full valence shell, which means they all have 8 valence electrons except for helium. So remember, the first energy level only holds a maximum of 2 electrons. Helium is full with having 2. But all of the rest of these have 8. Okay, so for this middle block of elements, so sometimes they're referred to as the transition metals or the D block, so you don't have to worry about that for now. It has to do with the orbitals where those electrons are. We'll look at that more in detail in grade 12. But for our transition metals, what's unique about these elements in the center is that some of them have the ability of having multiple valence electrons. So for example, right, iron can have 2 valence electrons or 3. So I know here it says that they can have 1 or 2, but to be honest, this is very, each element is unique in how many they have. So to help you with that, I kind of wanted to point out a little section of your periodic table. For the metals, okay, and it's important that you understand that what I'm about to talk to you about only works for the metals on the periodic table. In the top right-hand corner, so for example, if you take a look at cobalt, it has a 2 and a 3. So in grade 10, right, you had a periodic table of ions that was very easy to see what the valence electron count was. On your periodic table you're using this year and next year, you do have some information that can help you. So what that means is that cobalt, when it becomes an ion, can either become positive 2 or cobalt can become a positive 3. So the valence electron count can be different, right? So if you look at nickel, it can be 2 or 3 as well. Now you have to be mindful in that it has to make sense. So for example, iron here says 3, 2, or 6. Okay, the reason why you're going to have these weird numbers sometimes that won't make sense is because these are actually called oxidation states, not really ionic charges. So don't take this with 100%. Like it can only be 3, 2, or 6. Okay, so each element is unique. This is just meant to be as an aid to help you. So of course, it doesn't really make sense that iron's going to lose 6 electrons, but hopefully if you recall, right, iron can be positive 2 or positive 3 when it becomes an ion. So remember, all metals become positively charged because they're losing electrons. If you take a look here at some more examples, right? So tin can have a charge of 2 or 4, right? Positive 2 or positive 4. Gallium, 1 or 3. Lead, right? 2 or 4. But you'll notice that some don't have multiple options. So for example, indium, right, can only have a charge of +3. So these are meant to be as like a helper, so you can see which ones have multiple charges, which ones don't. Okay, so for the lanthanides and actinides, so remember technically, and you can see the stars here, these really fit in the periodic table in this location. You can also see that because if you look at barium, it's 56, and then it goes to 72. So it's like, well, what the heck happened to 57 to 71? So they are down here. Now, the reason why they are separated is more for aesthetic look. So the periodic table looks much more neat and together without having these two big rows kind of separating this all out. But more importantly, it has to do with the orbitals involved in those. So again, ignore this for now, but just so you know the reason why they are there, first of all for aesthetics, but also it matches up with the orbital location, which we'll talk about more in grade 12. Okay, so in grade 10, you learned about Lewis dot diagrams. So remember, we're no longer going to be using Bohr-Rutherford. We're focusing on Lewis only for this year, and even in grade 12, pretty much from here on out. As we get more complex in our structure, we're not going to be looking at Bohr-Rutherford pretty much at all. So remember that Lewis dot is only looking at the valence electrons. So this is why knowing what group it's in will help you know the valence, which will help you to figure out how to do the Lewis dot diagram. Okay, so one major rule when you are putting in your dots is that you must have the, so remember these are representing electrons. The electrons have to be fully separated into their 4 locations before you can begin doubling up. So if you notice here, we have 1, and then 1, 2, 1, 2, 3, 1, 2, 3, 4, and now we can start doubling up when we have 5. Okay, so just to show you what I mean by that, we'll take calcium, for example. Okay, so calcium is in group number 2, so it has 2 valence electrons. So this would be correct, or you can do it this way. But what's important is they have to be separated as far as possible. What is not correct is if we were to do this. Okay, so you want them to be as far apart as possible, and there are multiple ways of drawing these out. I'll give you another example. So let's take sulfur. Okay, sulfur has 6 valence electrons because it's in group 16. So we would do 1, 2, 3, 4, 5, 6. Right, so notice I had 1 in each of those locations before I doubled up. Or we could do 1, 2, 3, 4, 5, 6. Okay, so to be honest, not too picky in terms of like which ones you decide to double up. What matters is you need to have the 4 in place first before you begin your double up. Okay, so like really, let's say even something like this would still be correct. So like I said, the double up, where you begin your double up doesn't matter. What matters is that you have 1 in each side before you start that. So all of these would be correct, right? So what would not be correct is if I were to do something like this with my 6, right? That's incorrect. Okay, so here is an example showing you with going across the period. So group 1, lithium, group 2, beryllium, boron is in group 13, 14, 15, 16, 17, and then of course we have our noble gas of neon.